Okay, so there's a lot of details in this problem. First thing I want to do is draw a picture, just so we can have something to work off of. So, following the hints that we were given, it's roughly circular. It's symmetric over the y-axis here, but it's got a pinch on the sides. So it's like I'm going to draw a guitar body there. I don't know if that's actually right or not. Actually, that's going to be tough. Let me. Something more like that. Okay, so we're looking at the points 5, 2. Oh, well, this is going to be poor scale. That's fine. Okay, so 5, 2, and 5, -2. Those 2 points that are on this curve. Okay. So, to your question, how do we compute the unit tangent vector? Well, I'm going to take the given hint here, which says use the gradient vector to find normal vectors, and then we're going to rotate and scale. All right. So, notice what we have here is a function for which we are looking at a level set. Right? Does that make sense? Mm-hmm. Okay, so that function, I'm going to call this f, as we've often done. And so gradient of f, gradient of this capital F function, I can write on this picture, there's gradient of capital F. Right, and then over here, at the other picture, at the other point, it's going to be some other. Now, they're going to have different lengths. I mean, I don't know how long those vectors are, but they are both perpendicular to the curve, right? So, now the advice that we were given was to rotate and then normalize. Right? So, how do we rotate? Well, neat trick that you might remember from Chapter 1 is that if you want to take a vector AB, and if you want to rotate counterclockwise, so like for example, imagine that this is the vector I want to rotate counterclockwise, then you switch the coordinates, right, and then you put a minus sign on the first one. Okay. And it's just a neat, and you can confirm that this rotated because these two vectors have the same magnitude and their dot product is equal to 0. So they're perpendicular and of the same length, mm-hmm. So they're rotations. Does that make sense?
It makes sense.
Yeah, cool. So that trick will allow you to compute that vector, just a little quick rotate, mm-hmm. And then normalizing just means take that and divide it by its own magnitude, and that will give you your t vector. Is everybody happy with that? There's a bunch of little details, and I'll let you guys do the details there. Okay. Right. All right, now, oh, whoops, sorry. So now we get into the little differentials part. Okay, so we're going to consider 2 small pieces of this curve, and that fall in this thin slice, and the thin slice is between these 2 values of x, right? 5 and 5.001. Mm-hmm. I just made these up. So here's where 5 is. Clean up my mess. So that's 5, and there's x equals 5.001. Right. So this gives me 2 little pieces of curve. There's that little piece of curve, and there's that little piece of curve. That makes sense? Mm-hmm. Okay, and these 2 little pieces of curve are different. I mean, they're not reflections of each other. This surface is not symmetric over the x-axis, right? So I can't just say, oh yeah, they look the same. It's just upside down. They're not. They're totally different. Okay. Okay. And let's see here. The question then asks, oh yeah, so we observed that, so dx is 0.001. The absolute value of dx is 0.001 in each case, though, because, on each little piece, that's what the absolute value of dx looks like. they're the same because they have the same projection to the x-axis, and that's our interpretation that we're making of the absolute value of dx. Yeah, everybody happy? Okay. Right. Okay. Just don't forget that on this top piece of curve, it's going to the left because that's counterclockwise. On the bottom piece of curve, it's going to the right because that's counterclockwise. Right? Both of these are counterclockwise, but one's left, one's right. Okay. Right. So we're supposed to use these equations now to compute the vector differential. Let's find the dx vector for both of them. All right. And the length differential ds at the given points. All right. So I'm going to take advice, and so the dx vector, dx dy, is TDS. Let's write that down here. Okay. Now let me write this a little bit differently as dx vector equals dx dy, and this t vector has components. In fact, it's a unit vector, so I know it's going to be cosine and sine of some angles. Okay, so this is going to be cosine of some angle, sine of some angle, whatever those angles are. And then times ds. All right.
Sorry, how did you get that last part?
Yeah, so this is going to be a unit vector, right? This is a unit vector pointing in some direction depending on what theta is, right? And t is a unit vector pointing in some direction, so some way or another there's a theta that makes t equal to that.
Okay.
Yeah. Okay. All right. Now we're supposed to compute that. And here's the thing. All we know is dx. So let me start with what we know. This dx, and I guess maybe I'll... So that dx is 0.001-ish. So, I mean, plus or minus, depending on this and that. So by the way, let's start with the top. We'll worry about the bottom point later. Okay. So on this top point, don't forget we're going to the left, counterclockwise, but in this case that's to the left. And that means that dx is actually negative 0.001. That make sense?
Oh,
yeah. Okay. Right. And let's see here. And I know... Oh, by the way, we've already computed... I guess I didn't really need to write those as cosine theta, sine theta. We already computed... I'm just going to call that A and B, because we computed the t vector. Or you guys are going to compute the t vector. Yeah. So that means I know that, and I know that, and that means I can solve for ds. Right? Because minus 0.001 is a ds. Yeah. Is everybody good? Okay. All right, so here's the thing. Now, if you know ds, don't forget we know a and b, and that means you can compute dy. By looking at the bottom sort of equation there.
Yeah, how do we know ds?
Well, we know ds because we solved for it in the top equation. Right? So looking at this,
Okay.
then we know that, and that was computed previously, and so therefore we can solve for ds. Yeah.
Just to clarify, the ABs, those are the ABs of the t vector. We just computed.
Yeah,
so like
yeah.
the negative BA.
Yeah. That's right. Yeah.
Okay,
Yep. Right. Right. So now, basically, knowing this and knowing this helps me compute that, which along with that helps me compute that, and now I know my dx vector.
Okay.
Yeah. So it's kind of piecing things together. Yeah. Okay. Okay. So now that was all with this this top point in mind. Keep in mind that was going counterclockwise, namely left. But for the bottom one, counterclockwise is right, which just means that we're going to have a plus there. And same process. Now another difference, of course, is that this vector here is totally different. Right? It's a different point. It's got a different tangent vector. So, but the process is going to be the same.
Yeah.
Okay. All right. Okay. All right. And then of course ds is just the magnitude of the dx vector. So that's just Pythagorean formula. Everybody on board so far? Okay.
Wait, how is it the magnitude?
Well, it's literally, ds is the magnitude of the dx vector, and so square root of the sum of the squares,
Okay.
right? Yep. All right. Okay. So, is there any relationship between the values of dy or ds on these two pieces of curve? Well, that's a question to be answered after you've actually done these computations, but you're just going to look at the dy. Let me draw on the picture here. For the top piece, you're going to get some dy. For the bottom piece, you're going to get some dy, and is this at all related to that? No, they're totally different. Okay? It's not like one is the negative of the other or anything like that. They're just completely different things. Yeah. So the answer is no.
Because it depends on the curve, right?
Yeah, that's right. Because it depends on the shape of the curve and taking advantage of the fact that it's just not symmetric over the x-axis. So that little piece of curve and this little piece of curve, they really don't look the same. Mm-hmm. So yeah. So the dx's are the same. The dy's are different.
Yeah.
Okay. All right. So let's show that the values of f of x dx on the two pieces of curve are exact negatives of each other. All right. So, well, we've already agreed that on this piece, dx was negative 0.001, and on that piece, dx was positive 0.001. So the dx's are clearly negatives of each other. Mm-hmm. F of x depends only on x, and these 2 points have the exact same value of x. So if x is the same, then f of x is the same. The only thing that's different between the two expressions that you get for this at the 2 different points is that the dx's are negatives. Right. All right, and let's see now. Was there an f given? I don't think there was. No. Okay. All right, so let's see here. Suppose we're interested in computing the value of this line integral. Now, note this is a coordinate line integral, right? So it looks like a line integral. I guess it's kind of a line integral, but it's not ds. It's dx, right? So this is one of these weirdo notational things. Okay. So if we slice vertically, the suggestion is that what you get on that piece and what you get on that piece are exact negatives of each other. Right? So
that's exactly what we just did.
Yeah, that's right. It's exactly what we just showed. Okay. And so altogether, the idea is this: if you're interested in computing integral around the entire curve. Closed curve, by the way. Closed curve. F of x dx. And if you then take that curve and chop it up into little pieces, because that's what integrals are, right? But if you're careful, and if you chop it up by slicing like that, right, then you're going to get a bunch of little pieces, sure, but beautifully, even though that piece of curve and that piece of curve don't look alike, these two terms cancel, right? And then likewise, that little piece of curve and that little piece of curve, they don't look alike, and yet those two terms cancel. And so altogether, you get a bunch of terms, and they all pair up and cancel perfectly, thus giving you that this integral is 0. So this is kind of a Chapter 5 point of view. This is just really kind of an exercise in kind of an exploration of what do these coordinate line integrals look like and what do they mean. And I just wanted students to see that, just kind of see what they look like. You know, in this case, because that depends only on x, not y. That's why you get this cancellation. Yeah. Now, by the way, you might recognize this expression from today's lecture. Today's lecture, we showed that whenever you have a line integral around a closed curve of a function of x dx, Green's theorem gives us this exact same result without having to go through this argument. Right? So what we're seeing in this exercise is a sort of a coordinate line integral point of view on it, and today we saw the arguably much easier Green's theorem point of view. Is that cool? Is everybody happy?